Hello everyone, my name is Ratnadeep Bhattacharya and I am presenting my paper BLOC Balancing Load with Overload Control in the Microservices Architecture. But what are microservices? In the past, companies have typically deployed web services as a small number of applications in a multi-tiered structure. Some tiers might be replicated, like the blue component here. So we used a load balancer between the tiers to distribute traffic to the replicas. Then the trend changed to breaking down these applications to a smaller number of components. Finally, these components were deployed separately for ease of deployment and development, mostly using a virtual machine or a container for each service. This is the microservices pattern. However, this changes how we need to deploy load balancers. Instead of a single load balancer between the tiers, we now have each microservice with its own load balancer. This architecture, known as the sidecar or the request side load balancing, is heavily adopted in the industry because it prevents the centralized load balancer from becoming a bottleneck and simplifies deployment by packaging the load balancer with the application. But these load balancers may have completely different views of the backend load conditions, and they independently route requests to the backend service using only the information that is available locally to them. Join the shortest queue, or JSQ, has been established as a nearly optimal load balancing algorithm on server-side load balancers. In this algorithm, each request is routed to the backend with the smallest queue size. For example, here we see the next request being sent to the blue queue because it has the least number of requests. Since there is only one load balancer, it has a global view of the queue lengths of all the backend nodes and can make good decisions. Least connection is an adaptation of JSQ, which is popular in microservices. Least connection works pretty much the same way as JSQ, but since it doesn't know about the other load balancers, it only uses its own view of the backend queues. As a result, the least connection algorithm might not always select the least loaded backend server. For example, in this case, the next request might actually get routed to the green queue because the backend the upstream load balancers have very different views of the backend load conditions. Our research shows that least connections reliance on local information can have surprising effects. In microservices, each service can scale independently of all other services. In this experiment, we deployed a two-tier application and steadily increased the number of pods in the front-end layer from 1 to 40. And even though the workload and the backend pod number did not change, the response time distribution widened and the tail got longer. This result is surprising because we didn't expect that increasing the number of resources in the front end will result in the performance becoming worse. We ascribed this issue directly to the erroneous decisions made by least connection. As the number of front-end nodes increased, the routing errors made by the upstream service also increased. This is especially problematic when backend requests are expensive and bad decisions quickly cause overload. To prove our hypothesis, we deployed a Redis cluster in our environment, which acts as a global store of queue length information. Every upstream node, upon receiving a request, queries the Redis cache for the latest information, makes its decision, and updates the Redis cache about that same decision. We saw that this simple setup completely resolved the problem of the resource time distribution getting wider and tail latency getting longer. This is also shown in this graph where the orange line representing the single front-end case overlaps with the green line representing 40 front-ends using the Redis cache. Thus, having global information fixes the widening of the response time distribution. We further tracked how the load was being distributed across the backends. We found that variance of load distribution increased significantly using 40 front-end nodes versus one front-end node. The global Redis store drastically reduced that variance for the 40 front-end nodes. However, there are several issues with maintaining a global state. It requires a considerable number of messages being passed around in the network. It may also require very stringent convergence guarantees. Overall, it leads to very expensive and complex designs. In our simple and small setup itself, we are making multiple API calls per request. In our paper, we try to find a better way to resolve this. We aim to build self-managing microservices which are able to determine load balancing policy without requiring a centralized load balancer. We do so by using feedback signals between downstream and upstream nodes. Using this feedback signal, we build a probabilistic indicator of server capacity and use overload control mechanisms to make the system automatically respond to overload conditions in a seamless manner. Our work is based on two complementary overload control techniques. Active queue management, or AQM, allows backends to reject requests in order to prevent excessive queue buildup. However, by itself, AQM may lead to an unacceptably high level of failed requests. Next, we use rate limiting. This is done by frontends in response to back pressure from downstream. However, if not done carefully, rate limiting can cause the system to upsize or penalize the wrong service. To combine these two approaches more effectively, we introduce the concept of the confidence chip. A chip is a measure of remaining capacity on a downstream and is piggybacked with a response message. The probability of the downstream granting a chip is proportional to its queue size. So more loaded a server is, less likely it is going to send a chip. We also reserve 20% of the server's capacity for upstream nodes that have not interacted with this backend for a while. Thus, confidence chips act as a way for backends to provide feedback to frontends without requiring explicit coordination messages or any centralized data store. Each upstream node maintains a list of active and inactive downstream nodes. These lists are local and are not coordinated in any way. Downstream nodes for whom the upstream has no chips are considered to be inactive. Every inactive downstream node is also associated with an inactive timer, which is started when the node is marked inactive. Now, we want to select a server for routing the next request that is a part of the active list. However, if an inactive server has a low queue size and the timer associated with it has expired, then we can decide to probe that inactive server by sending a single message. This lets us rate limit in a smart way and keeps the metadata of each of the backend nodes relatively fresh. When a request reaches a particular downstream and its queue is not full, the downstream serves the request and can choose to send a confidence chip back with a response message. This updates the metadata for that particular downstream on the upstream that generated the message. On the other hand, if the queue of the downstream is full when the request is received, the downstream will reject the message, and upon receiving that rejected message, the upstream invalidates all chips for that downstream, places that downstream in the inactive list, and starts the inactive timer. The rejected request is then rerouted to a different backend. This particular upstream can mark this downstream active if it receives a reply from an outstanding request with a chip, or it can be probed by sending a single request once the inactive timer has elapsed. server capacity forms the upper bound of queue size at every node and thus informs the upper bound of the queuing delay at that node. This is a parameter which can either be configured manually or BLOC can estimate it based on queue length data at runtime. To summarize, BLOC provides simple signals between downstream and upstream nodes to improve autonomy in distributed microservices. Downstream nodes signal with confidence chips and rejection messages to inform upstream nodes of their approximate capacity. The upstream nodes then use these signals to create their active and inactive lists for rate limiting. By redirecting rejected requests, upstreams can quickly shift load away from overloaded servers. Overall, these techniques help us build self-managing microservices that automatically respond to overload conditions and balance load better. For the test setup, we built our own microservices architecture generator, which runs dummy functions like sleep to simulate computation. In our testing, we used a front-end service layer with the number of nodes varying from 1 to 40 and a back-end layer with 10 nodes. Requests are admitted through a separate gateway service. Our results show that BLOC can provide an extremely narrow response time distribution. In this graph, the green line is BLOC with 40 front-end nodes, which is narrower than least connection with a single front-end node. It is also interesting to note that the median response for all these distributions is similar. This stresses the importance of considering the full distribution when testing a system like this, rather than only considering mean or median response times. High tail latency is especially damaging for microservices since one client request may cause a large fan out to different services. And if any one of those services has a long tail, it will impact the entire request. BLOC relies on its capacity estimate to control its rate limiting. Here we show that a carefully tuned capacity estimate results in the narrowest response time distribution. The green line is our dynamically measured capacity tuning approach. This is still better than least connection and a poorly tuned capacity estimate, but there is still more work to be done here. We think we can improve this further, and that is going to be the focus of our future work. We have evaluated BLOC for components with different service costs, and we see that for heavier requests, more than 100 milliseconds, the overall response time distribution width is improved by as much as 96%, and the tail latency gets improved by as much as 50%. Lighter requests also see some benefit, but that is not as drastic as for the heavier requests, because with the heavier requests, least connection gets easily overloaded a lot, resulting in these high gains. Because with heavier requests, least connections decision making using local state is catastrophically adding up. To summarize, BLOC provides simple signals between downstream and upstream nodes to improve autonomy in the distributed microservices. Downstream nodes signal with confidence chips and rejection messages to inform upstream nodes of their approximate capacity. The upstream nodes then use these signals to create their active and inactive lists for rate limiting. By redirecting rejected requests, upstreams can quickly shift load away from overloaded servers. Overall, these techniques help us build self-managing microservices that automatically respond to overload and balance load better.